Okay, let's start with the basics of event-driven architecture. It's all about how applications talk to each other. Instead of direct calls, services communicate by publishing events, essentially broadcasting what's happening. Think of it like a busy town square where announcements events are made and people who care listen in. Services that make these announcements are called producers, while those listening are consumers. There's usually an event bus or broker, something like Kafka or RabbitMQ, that handles the delivery of these events. Events themselves are just data records representing changes, like a new user being created or an order being placed. Because they are immutable, you can be confident they won't change once sent. EDA offers some major advantages. It promotes independence between services, making scaling and adapting to changes much easier, and it allows for really fast reactions to events. Okay, let's talk about what makes an event-driven architecture work. At its heart, it's built around 5 key components. First, you have your event producers, which are the services or applications that actually create something like a new user registration or a purchase. Then there's the event router or message broker. Think of it as the post office for these events. It receives them and directs them to where they need to go. Next, we have the event consumers, which are the services that listen for specific events and take action based on what happened. Events themselves are just lightweight packets of data, essentially information about what occurred. And finally, we have an event schema registry. It's like a blueprint, making sure everyone's talking the same language when it comes to event data. Okay, let's talk about events and event-driven architecture. Simply put, an event is a signal that something significant has happened within your system. It's not just data, it's the occurrence itself. Events are like little notifications saying, hey, something changed. They don't change once they're created, they just exist. Think of things like a new user signing up, an order being placed, or even a sensor reading going off the charts. These events trigger other parts of your system to do their thing, and they generally happen less frequently than regular data updates. They are designed for speed and impact. Okay, so let's tackle this common question. Basically, an event is just a notification. It's like saying something happened. It's about the state of things at a particular moment, and that state can't be changed. Think of it as, hey, someone placed an order. Now a message is different. A message is more like a request or a response. It tells another service to do something based on what happened. It's saying, okay, now I need you to update the inventory because that order was placed. Events are passive. Messages are active. Okay, let's break down the roles of producers and consumers within an event-driven architecture. Producers are like publishers. They're components that notice something significant happening, like a new order being placed or a user signing up, and then they create what we call events. These events are basically messages containing all the relevant information about that change. Now, consumers are the listeners. They are services that specifically subscribe to these events. When an event is published, the consumer receives it and does something, maybe updating inventory levels or sending a welcome email. Think of them as actively responding to what's happening in the system. Okay, let's talk about event brokers. In the world of event-driven architecture, an event broker is essentially a message bus. It's like the central nervous system for your application. Producers, which are often services or components that detect something happening, publish events to this broker. The broker then intelligently routes those events only to the consumers that need them. It's all about decoupling different parts of your app so they can react independently and scale more effectively. Some common examples include Kafka and RabbitMQ. Okay, let's talk about why event-driven architectures are so popular. The biggest advantage is probably loose coupling. It means different parts of your system can work independently without being tightly connected. This makes scaling much easier because you can add more instances to handle increased traffic. Plus, events lead to really fast responsiveness, meaning the system reacts quickly to what's happening, improving user experience. And finally, it's incredibly flexible and maintainable. Adding new features or changing existing ones is much simpler when things aren't so tightly bound together. Okay, let's talk about some of the common challenges you'll face when building an event-driven architecture. It can be tricky to get right. The biggest one is often just how complex things can become quickly. You have lots of independent services talking to each other through events. Debugging becomes a real pain without good tracing tools and correlation ID. Schema evolution is another big deal. Making changes to your event structures needs careful planning so you don't break consumers that rely on the old format. And because events can be processed multiple times, it's critical to ensure your processes are idempotent, that they produce the same result regardless of how many times they run. Finally, remember, EDA often leads to eventual consistency, meaning data isn't always immediately up to date everywhere. You need to design your application accordingly. Okay, let's talk about event sourcing. Imagine you're tracking every change in your system instead of just the current state. That's essentially what we do with event sourcing. We store everything as a series of events like order created, product shipped, or payment received. These events are immutable, meaning they can't be changed after they happen. We keep them in an event store, which is like a detailed history book for our application. You can then replay these events to rebuild the state at any point in time. It's a really powerful way to make systems more flexible and easier to understand, especially when it comes to debugging or figuring out how things changed over time. Okay, let's dive into a key difference between event-driven architecture, specifically how they differ from the traditional CRUD model. CRUD is what most of us are familiar with, creating, reading, updating, and deleting data directly in our databases. It's straightforward, but it can be tricky to track changes over time and reconstruct past states. Event sourcing flips this on its head. Instead of storing the current state, it keeps a complete log or sequence of every single event that's ever happened within the system. It's like an immutable audit trail. You're not directly manipulating data, you're rebuilding it by replaying those events. This makes it incredibly powerful for things like auditing, debugging complex scenarios, and even supporting temporal queries asking what was the state of this account at 3 p.m. yesterday, which is hard with a traditional CRUD approach. Okay, let's talk about message queues. They are a really important concept in event-driven architecture. Basically, they are like a middleman that allows different parts of your system to communicate without being directly connected. Imagine you have one service that needs to send an email when a new user signs up, and another service that handles processing user data. A message queue lets them talk indirectly. One service puts the new user sign-up message into the queue, and the other service picks it up later. This separation makes things much more flexible, easier to scale, and more reliable because messages aren't lost if one part of the system is temporarily down. Okay, let's talk about message topics. In event-driven systems, messages are how different parts of the application communicate with each other. A message topic is like a category or label for those messages. It helps us group related events together. Think of it like organizing emails into folders. You'd have folders like work, personal, and receipts. Each topic will contain events that belong to that area, such as order updates, payment confirmations, or new user registrations. We use these topics so we can send the right messages to the right services. Okay, let's talk about messaging patterns and event-driven architectures. We often encounter point-to-point and publish-subscribe models, and they are quite different. Point-to-point is like a direct phone call. One sender directly communicates with one specific receiver. It's simple to set up initially, but as things grow, it can become really complicated and tightly coupled. You have to ensure the sender knows exactly who needs to receive the message. Now, publish-subscribe is more like a newspaper. Publisher just broadcasts an announcement. They don't know who will read it. Subscribers then listen for any messages related to specific topics. This means that components are loosely coupled, making the system much more flexible and easier to scale. Okay, let's talk about some of the key technologies we use when building event-driven systems. Think of tools like Kafka, which is a really powerful platform for handling streams of data in real time, perfect for things like tracking orders or detecting fraud. Then there's RabbitMQ, another popular message broker that works with different messaging formats. Redis streams are also gaining traction because they're super fast and can handle lots of events. And don't forget Amazon SQS, a managed service that simplifies sending messages between different parts of your application. It's important to understand the strengths of each tool so you can pick the best one for your project. Okay, so let's talk about Kafka. It's a really important piece of the puzzle when we're building event-driven systems. Essentially, Kafka is like a super reliable post office for your applications. It allows different parts of your system to communicate without being directly tied together. It uses a publish-subscribe model, where services publish events. Think of them as notifications, and other services subscribe to the events they need. Because Kafka stores these events reliably, consumers can process data whenever it's convenient for them, even if the producers are busy. This decoupling is what makes event-driven architecture so powerful, because it lets you build systems that are much more flexible and scalable. Okay, let's talk about RabbitMQ. It's a really important piece of the puzzle when we're building event-driven systems. Think of it as a super reliable post office for your events. Producers, which are like the people sending out messages, simply drop their events off at RabbitMQ. Then consumers, that's where your different services pick up those events and do what they need to do. The cool thing is, producers don't have to wait around for a response, they just send it and move on. RabbitMQ handles getting the message to the right place. It supports really flexible routing, so messages can go to many places based on different rules. You'll often see it used in things like order processing. When an order is placed, various services need to react, updating inventory, handling payments, scheduling shipping. It's all about decoupling these services and making the system more robust and scalable. Okay, let's talk about event streams. Essentially, an event stream is like a continuous log of things happening in your application, a timeline of events. Each event is a single occurrence, and they arrive one after another, maintaining their original order. It's super important to remember that these events are immutable, meaning once they are sent, you can't change them. They just keep flowing. These streams are usually handled by something like Kafka or RabbitMQ, which provides the infrastructure for managing all this flow. Okay, let's dive into stream processing. It's a really crucial concept when talking about event-driven architecture. Basically, instead of waiting to collect all your data in batches, you're constantly receiving and working with the information as it comes through. It's like having an instant reaction system for your events. You can think of it as processing each customer order immediately when it's placed, rather than waiting an hour to analyze everything at once. This gives you those immediate insights and allows you to take action right away. Okay, let's talk about how event-driven architectures actually make systems much easier to scale. Imagine you have a large e-commerce platform. In a traditional setup, if one part of the system gets overloaded, say, during a big sale, it can slow everything down. With EDA, each service operates independently and communicates through events. If the checkout service is busy, it doesn't block other services like product catalog or shipping. Each can scale up or down as needed, creating a much more resilient and flexible system that handles increased traffic smoothly. Okay, let's talk about how event-driven architecture helps us create more loosely coupled systems. Basically, instead of services constantly calling each other directly, which creates tight dependencies, they communicate by publishing and subscribing to events. This means a service doesn't need to know who is going to use the information it sends, it just publishes an event. And because services are only interested in the events that are relevant to them, they can be updated or scaled independently without causing problems for other parts of the system. It's like a notification system. One service tells another something happened, and the second service reacts accordingly. That inherent separation makes things much more resilient too. Okay, let's talk about eventual consistency in event-driven architecture. It's a really important concept to understand, and it's often where people get tripped up. Basically, eventually consistent systems don't guarantee that you'll always see the absolute newest data immediately when you read it. Instead, they promise that if you make a change in event, then eventually all subsequent reads will reflect that change. It's like updating an order total in an online store. One user updates first and another shortly after. Both users will ultimately see the correct amount, but there might be a brief delay. Eventual consistency allows for systems to be more scalable and responsive because it avoids having to immediately synchronize all data across every node. It does introduce some complexities, like needing strategists to handle conflicting changes and deciding how many versions of data you'll return when someone reads. Okay, so let's talk about how errors are handled in event-driven systems. The core idea is that because everything happens asynchronously, you can't just stop and handle an error like you would in a traditional system. Instead, we need to build in some safeguards. One common approach is to embrace eventual consistency, meaning things might not be perfectly consistent immediately, but they will eventually become so. We also use techniques like compensating transactions, where if one service fails during a process, another service kicks into action to undo any changes that were already made. Dead letter queues are really important too. They're used to capture events that couldn't be processed successfully and allow us to investigate what went wrong later on. Circuit breakers help prevent cascading failures by temporarily pausing requests to a problematic service. And finally, ensuring your services are idempotent, meaning they can handle the same event multiple times without causing problems, is really crucial for reliable retries. Okay, let's dive into dead letter queues. Think of them as the error handling zone for your event processing system. They catch messages that are failing to be processed by your consumers, essentially messages that aren't being successfully handled. This prevents those problematic messages from getting stuck in a loop, causing all sorts of headaches. When a message repeatedly fails, it gets moved to the DL queue, where developers can then investigate and resolve the root cause, whether it's bad data or a service issue. It's really about building more resilient and manageable systems. Okay, let's talk about subscriptions in event-driven systems. They come in two main flavors: durable and non-durable. Non-durable subscriptions are like sending a quick message. They're great for things you really want to see immediately, but if the receiver isn't available, the message is just gone. This works well for notifications or real-time updates where immediate delivery is key. On the other hand, durable subscriptions are more reliable. They hold on to messages until they've been successfully processed. So, even if a consumer has an issue or needs a little time to catch up, it can resume processing from where it left off. This is vital for things like order processing or financial transactions, where you absolutely need to ensure every event gets handled no matter what. Okay, let's talk about message acknowledgement in event-driven architecture. Think of it like this. You send out an event, maybe an order was placed, or a new user signed up, and you want to make sure the receiving service actually got that message and handled it correctly. Without acknowledgements, you're basically sending things into the void. There are two main types: immediate acknowledgement, which is sent right away after the consumer receives the event, and final/complete acknowledgement, which only happens after the consumer has fully processed the event, like confirming a database update was successful. Producers use these acknowledgements to know when an event is truly handled. Let's talk about message order in event-driven systems. It's surprisingly important. You can't just assume that events will arrive in the same order they were produced, because producers aren't always perfectly synchronized. One common strategy is to design your handlers to be idempotent, meaning they can handle duplicate messages without causing issues. Another option is to add sequence numbers to each event, letting consumers sort them based on those numbers. For more critical operations requiring strict ordering, you might consider using distributed transactions or sagas, or even incorporating timestamps and an ordering key into the events themselves. The right choice depends on your specific needs, but always keep idempotency at the forefront. Okay, let's talk about idempotency, a really important concept when we're diving into event-driven architecture. Basically, it means you can process an event multiple times without changing anything beyond the initial effect. It's like ordering pizza online. If the system tries to process your order twice, you still just get one delicious pie. Why is this so crucial? Well, EDA systems often rely on asynchronous processing and retries when things go wrong, so idempotency ensures that we don't end up with duplicate actions or data, keeping our systems reliable and consistent. It's a key piece for building scalable and robust event-driven applications. Okay, let's talk about how to tackle testing these cool event-driven architectures. It's a bit different than traditional testing. You can't just follow a linear path. The key is to focus on the events themselves. Make sure they're being emitted when you expect them, and that downstream services are reacting correctly. We use things like contract testing to ensure everyone agrees on what an event should look like. Then we test how things work together by simulating messages flowing through the queue. Finally, end-to-end tests really help us verify the whole chain of events is working as planned, and you can even mock out parts of the system to isolate specific issues. Okay, so let's dive into event schemas. They are really key to making sure everything works smoothly within an event-driven architecture. Essentially, an event schema is like a detailed blueprint for what data makes up each event message. It defines exactly what fields are included, the type of information in each field like numbers, text, or dates, and even sets rules about how that data should be formatted. Why do we need this? Well, it's all about making sure different parts of your system, let's call them services, can talk to each other effectively. By having a common understanding of what an event looks like, they can trust the information being sent and received. This leads to better data quality, easier debugging, and even more flexibility as you evolve your architecture over time. Let's talk about how schemas change in event-driven systems. It's a really important consideration. As your applications evolve, the data you're sending as events might also need to grow. Initially, you might only have a customer's name and email address, but later you add things like their full address or phone number. The trick is making sure all your services can still process this new information without breaking anything. There are a few ways to handle this. One is to just add the new field as an optional part of the event holder. Consumers that don't need it simply ignore it. Another approach is to make sure all consumers can deal with every single possible field, even if they aren't actively using them yet. And finally, a really good practice is to use a schema registry, something like Apache Avro or Confluent Schema Registry. This lets you keep track of different versions of your schemas and helps manage compatibility automatically. When thinking about this, it's important to consider how much work it will take for your consumers to update, whether you need to migrate existing data, and how you'll version your events. Okay, let's talk about correlation ID. They're super important when you're building event-driven systems. Imagine you have an e-commerce application and a user places an order. That single order might trigger events in your inventory service, payment gateway, shipping service, and maybe even your marketing automation platform. Without a way to tie all those events together, debugging problems or understanding the full customer journey becomes really difficult. Correlation ID are like unique identifiers for each of those events. Think of it as a tracking number for this order. Every event generated in your system should include its own correlation ID, and then other services can carry that ID along with their response. This lets you trace the whole process back to the original user action, making debugging much easier, providing better audit trails, and even helping you monitor performance across different parts of your system. Okay, so let's talk about compensating transactions. In a complex event-driven system, things can sometimes go wrong. An event might fail mid-process. We need a way to clean up any partial changes. Compensating transactions are like an undo button for your entire sequence of events. They're designed to reverse the effects of a failed transaction, ensuring that your system stays in a consistent state. Think about an online order. If payment fails after inventory is reduced, we can't just stop the order. We need to put the inventory back and potentially issue a refund. Compensating transactions are all about making sure those side effects are handled, and they rely on operations being idempotent so repeating them doesn't cause problems. Okay, so let's talk about Event Storm. It's a really powerful way to get everyone on the same page when you're building an event-driven system. Basically, it's like a massive brainstorming session focused entirely on what is happening in your business. We gather together with developers, product folks, and people who actually know the domain, and we just start writing down every single event that can possibly occur. It's about capturing all of those things that trigger changes within your system. Then we add commands, which are the actions that cause those events to happen. And finally, we layer in context the information needed for each event or command to make sense. It's a fantastic way to build a shared understanding and spot potential issues early on. Okay, let's talk about the core difference between synchronous and asynchronous communication. It's really important in event-driven architectures. Synchronous is like a direct phone call. You send something out and wait for an immediate answer back. It's simple, but can slow things down if the other person is busy or doesn't have the information right away. Asynchronous, on the other hand, is more like leaving a message. You drop it off and move on. The client isn't stuck waiting around. This makes systems much more scalable and resilient because they don't all need to be actively engaged at once. Okay, let's talk about CQRS and how it fits into event-driven architecture. Imagine you have a system where users can create new customers. In traditional architectures, this would likely involve updating multiple databases simultaneously, which can be slow and prone to errors. CQRS changes that. It separates the create customer action, a command, from simply retrieving customer information, a query. So, when someone creates a customer, it triggers an event like customer created. That event then travels through an event bus, where other services subscribe to it and react accordingly, maybe updating inventory or sending welcome emails. EDA provides a mechanism for this event propagation, and CQRS gives us a clear structure and separation of concerns for managing those commands and their associated events. Okay, let's talk about where event-driven architecture truly comes into its own. Think of it like this: instead of services constantly asking each other, do you have the information I need, they just announce when something's happened and let others react. E-commerce is a great example. When an order is placed, a whole chain of events kicks off: inventory updates, shipping notifications, payment processing, all happening independently. Then there are real-time apps like social media or chat that rely on constant streams of events to deliver information instantly. And don't forget IoT. Think about sensors sending data. EDA lets you handle the volume without bogging down a central server. Okay, let's talk about securing event-driven systems. It's a really important consideration. Because these architectures are so distributed, you need to think differently than you would with a traditional application. The key is to focus on protecting those events themselves and who can access them. We want to ensure that only authorized services are sending messages out and receiving data, and we absolutely must encrypt the message itself as it travels around. Validating event schemas, making sure they match what's expected, is crucial. And finally, don't forget about monitoring those dead letter queues. Anything stuck there could be a sign of a security problem or a configuration error. Okay, let's talk about the downsides of event-driven architecture. While it's fantastic for building scalable and decoupled systems, it isn't a silver bullet. First off, EDA can add complexity. Managing those event flows becomes quite involved. Debugging asynchronous events is trickier than tracing linear processes. You also need to think carefully about consistency. EDA often uses eventual consistency, meaning data updates might not be immediate across all services. This isn't always ideal and needs careful consideration for your application's specific requirements. Testing can also be a challenge because of the way events work asynchronously, so you really want to get good at mocking those events. And finally, monitoring becomes more crucial. You need solid tools to track event flow and pinpoint any bottlenecks. Ultimately, EDA is best suited when you're building systems with lots of independent services that need to scale easily, or for complex workflows where near real-time updates are important. Okay, let's talk about fan-out messaging. It's a really key concept in event-driven architecture. Essentially, when one event happens, it doesn't just go to one place. It branches out and triggers multiple different services or components independently. Imagine a river splitting into many streams. That's the idea. Each stream handles the event in its own way, which makes our system more scalable, resilient, and easier to change because each part is loosely coupled. Okay, so let's dive into how we handle failures in event-driven systems. Retrying messages seems straightforward, but it needs careful thought. The biggest challenge is idempotence, making sure our message only gets processed once, even if retries happen. Then there's back pressure. Too many retries can overload your services. We also need to consider how to handle failures consistently across the entire system. So, we're going to look at strategies like using unique identifiers for messages, implementing exponential back for the little randomness to avoid overwhelming systems, and crucially, setting up dead letter queues to catch those messages that are repeatedly failing so they can be investigated. Finally, circuit breakers can help protect your downstream services from getting overloaded. Okay, let's talk about poison messages. They're a really important concept in understanding event-driven architectures. Think of them as an emergency stop sign for a consumer. When a component can't process an event anymore, it sends out a poison message. This prevents any downstream issues from arising because the system knows there's a problem that needs to be addressed. It stops a single failure from bringing down everything else. They are used to signal a deadlock and often trigger a separate team to investigate and fix the issue. Let's talk about back pressure in streaming systems. Think of a really busy factory floor. If one machine starts producing way faster than the others can handle, you quickly get a bottleneck. That's essentially what happens when a producer is sending data to a consumer at a much faster rate than the consumer can process it. Back pressure is like putting a gentle brake on the fast producer, telling it to slow down and let the slower side catch up. It's all about preventing overwhelming the downstream services and ensuring no messages get dropped. Okay, let's talk about microservices choreography. It's a really interesting pattern when it comes to how your services communicate. Basically, instead of one service telling the others what to do like an orchestrator, each service acts independently, responding only to events that are published by other services. Imagine a dance where everyone just knows their part and reacts to the music. There's no conductor in charge. It's about keeping things loosely connected and avoiding any single point of failure. Okay, so let's talk about orchestration versus choreography in event-driven systems. Think of orchestration as having a conductor leading an orchestra. There's one central entity, the orchestrator, that tells all the other parts what to do and when. This is great for structured processes but can become complex if you have lots of steps and dependencies. On the other hand, choreography is like a group of dancers who are improvising together. Each dancer responds to the actions of others without needing someone to tell them exactly what to do. It's inherently simpler and more resilient because there isn't a single point of failure or control. Okay, let's talk about event-driven microservices. Essentially, it's a design pattern where services don't directly request information from each other. Instead, they react to events like an order being placed or a payment being received. Each service is independent and publishes events when something happens. These events are then routed to the appropriate consumer services via an event bus, which helps maintain flexibility and makes scaling easier. It's all about loose coupling and asynchronous communication. Okay, let's talk about how we keep an eye on things when events are bouncing around in a distributed system. It can get tricky fast. The key is tracing. Think of it like a breadcrumb trail that follows each event as it moves through different services. We use tools like Jaeger or Zipkin to build these traces, showing exactly where the event originated and how it traveled. Correlation ID are super helpful too. They're kind of like identifiers attached to events, linking them together even if they come from different parts of the system. And don't forget about logging and metrics. We want a central place to collect all this information so we can see things like event volume, how long it takes for events to move through the system, and any errors that pop up. Schema validation is also important. Ensuring events have a consistent format helps us spot problems early on. Okay, let's talk about Kafka versus RabbitMQ. Both are fantastic message brokers, but they are built for slightly different jobs. Think of Kafka as a super efficient data pipeline. It's designed to handle massive amounts of streaming data and is really good at things like tracking events over time. RabbitMQ, on the other hand, is more traditional. It's typically used when you need reliable delivery guarantees, like ensuring that a message gets through even if a system hiccups. Kafka is all about scale and speed, while RabbitMQ prioritizes strong reliability. Okay, let's talk about designing events. It's super important to create clear contracts for each event. Think of it as a specification that everyone involved needs to understand. This includes the event name itself, and importantly, only including the absolutely necessary data in the schema. We should also consider versioning our schema so we can make changes without breaking existing consumers. When designing the schema itself, using something like JSON schema or protocol buffers is a great practice for standardization and validation. And finally, sticking to a consistent naming convention will really help maintain clarity as your event-driven system grows. Thank you for watching.